Welcome to the hot seat. Picture this. You're sitting in a high-stakes technical interview. The clock is ticking, and the interviewer presents you with a classic, seemingly straightforward challenge. Well, today's explainer is going to equip you with exactly what you need to absolutely conquer the longest consecutive sequence algorithm problem. We're going to break down the mechanics, look at the common traps, and arm you with the ultimate elegant solution. Okay, let's dive right into our roadmap for this explainer. We've got 5 sections today. 1. Decoding the problem. 2. The brute force approach. 3. A better way using sorting. 4. The optimal set solution. And 5. Comparing the complexities. All right, section 1. Decoding the problem. So the prompt asks us to find the longest consecutive sequence. What does that actually mean here? Basically, we're looking for numbers that follow each other in sequential mathematical order. But the catch is, the array you're handed could be completely chaotic. The numbers can be totally jumbled up. Our job is to ignore all that visual noise and find the mathematical chain hidden inside. Let's ground that in some concrete numbers. Look at this example array. 100, 4, 200, 1, 3, 2. I mean, it looks like a random mess, right? But if you look closely, you can form a sequence of 1, 2, 3, and 4. Now, you can't pick a 5 because, well, it's just not in the array. We have 100, but no 101 or 102. So the longest continuous chain we can possibly build from this specific array is exactly 4 numbers long. And our goal? Return that number, 4. Moving on to section 2, the brute force approach. This is the naive solution, the natural first instinct that acts as the starting line of the interview. Step 1, you just pick an element, any element. Let's call it X. Step 2, you manually do a linear search through the whole array, asking, hey, are you X plus 1? If you find it, awesome. Step 3, you increment your counter and start a whole new search looking for X plus 2. You keep doing this exhausting, repetitive searching until you hit a dead end, and then you just start the whole process over for the next number. And this brilliantly illustrates exactly why this first approach creates a massive bottleneck. The time complexity here is big O of n squared. Think about it. For almost every element, you're potentially scanning the entire array all over again. It's incredibly redundant and, performance-wise, just way too slow. Now, to be fair, your space complexity is big O of 1. You aren't using any extra memory, which is fantastic. Your memory usage is literally perfect. But let me tell you, your interviewer is sitting across from you shaking their head at the speed. That extreme n-squared time complexity is a glaring red flag, and they are immediately going to ask you for an optimization. Which brings us to section 3, a better way, using sorting. So sorting actually clubs the consecutive numbers together. Suddenly, that messy array is neatly ordered. From there, it's just a simple iteration. You track a variable called last_smaller. If the element you're currently looking at is exactly 1 more than your last smaller, boom, you increment your count. If it's the exact same number, a duplicate, you can safely ignore it. And if the sequence breaks, you just reset your count and start a brand new chain. Just look at the massive mathematical improvement here. We went from a sluggish n squared down to n log n time complexity, which is basically dictated by the time it takes to sort the array first. You're making real progress in the interview. But here is the climax of the interview. The interviewer leans in, they look at your beautifully sorted array, and they drop the ultimate high-pressure question. Can we do this without distorting the original array? And can we do it in strictly linear time? They want big O of n. Let's move to section 4 and see how this builds into the optimal set solution. The setup here is incredibly elegant. Step 1, you take all the elements from your array and dump them into an unordered set, or a hash set, depending on your language. Why? Because sets allow for big O of 1 lookups. They magically eliminate the need to manually search the array. Once your set is built, step 2 is to simply iterate through it, and step 3 is to look for those sequential increments. But wait, if we just start checking every number sequence in the set, aren't we basically doing the brute force all over again? So I want to pose this crucial logical question to you right now. Why on earth would you start checking a sequence from the middle? So the crucial point is this ultimate hack. You only start counting a sequence if the number you are looking at has no preceding number in the set. If you're standing on a number x, you just ask the set, hey, does x minus 1 exist? If it does, you're in the middle of a sequence. Don't waste your time counting. You only start your engine if x minus 1 does not exist. That proves you are at the true starting line. Let's do a quick dry run of this flawless logic. You hit the number 100 in your set. Is 99 there? No. So you start counting. 100, 101, 102. Perfect. Next, you look at the number 1. Is 0 there? Nope. So you start counting. 1, 2, 3, 4. But then you look at the number 2. Does 1 exist in the set? Yes. That means 2 is the middle of a chain, so you skip it entirely. When you look at 3, it has a 2, skip it entirely. By identifying the starting lines, you totally eliminate redundant checks. And boom, this dramatically shifts our time complexity. Because of this hack, you do exactly n insertions to build the set, and then, at an absolute maximum, you're doing 2n lookups. N plus 2n is 3n, which, when you drop the constants, gives you a triumphant linear time complexity of big O of n. You've answered the interviewer's hardest question perfectly. Finally, Section 5, comparing the complexities. I want you to treat this table as your ultimate cheat sheet. Just look at the journey. We started with brute force n squared time, perfectly no extra space, but way too slow. We leveled up to sorting, n log n time, much faster, but it distorted the array. Finally, we achieved the optimal solution with the unordered set. Yes, we had to trade a bit of space, taking up big O of n memory to build that set, but in exchange, we unlocked maximum, non-destructive, strictly linear speed. Understanding this algorithm is a massive win. But the real takeaway here, it's the shift in perspective. That clever little hack we used with the set isn't just a trick for this specific problem. It's a completely new way of thinking about efficiency. So I'll leave you with this. What other impossible-seeming algorithms out there can be unlocked simply by pausing, stepping back, and asking yourself, am I actually starting from the right place? Keep that mindset with you, and you'll be unstoppable.